Hello, every now and then somebody tells me I should get into 3D printing, so I thought, you know what, maybe I will. And I ended up building my own machine to do that, and it takes some of this metallic filament and it brings it close to the hot end. See, I know all the terminology now. And it extrudes a little bit of the filament onto there in a very careful computer controlled fashion to build up some three-dimensional structure, just like that. The reason I wanted to have a machine like this is because I'm starting to have more and more of these IO mixer boards to assemble, or at least partially assemble. So that's how they arrived to me from JLC PCB. And to get them into this state, we need to add 112 pins, which I've been soldering manually so far. And I actually don't mind doing that once in a while, especially after I made a jig, or not this one. This is my first one. These holes turned out to be too big, and so the idea is you'd put the pins in there and then you'd lay this board on top and everything would be all ready to go and you could solder around it in one fell swoop. And these holes were a little bit large and the pins just wouldn't sit in there properly because you've got to line up 112 pins at the same time, right? And my next attempt, I'll show you a little bit more about this later, was out of aluminium for longevity, and the holes are a little bit smaller. This works much better. And with this, it's actually not really a huge deal to solder one every now and then, but I still, if you've got 8 or 10 to do all in a row, then it is kind of a chore still. So I designed all the parts for this in Onshape, and this is how I envisioned it being, at least right at the beginning before I'd tried any of these motors. So underneath here we have two NEMA 11s, and then on the back here we've got a NEMA 8 and another NEMA 8, and these turned out to be pathetic. So we'll just forget about this design. So this is roughly what I've ended up with. The bottom is pretty much the same as original, but the top had to be beefed up quite a bit. So we're using a NEMA 14 there, and I've had to use NEMA 17s for all the other motors as well. So everything needed to be quite a bit stronger than I had originally pictured. But I don't think I'll look at the CAD design too much here because we're going to see plenty of the actual thing. And I also haven't really finished. This solder reel is going to have to come up a bit, so it's not going to end up quite like this anyway. So this build has been in progress for a few months, and initially I didn't really record any commentary or anything. I just turned the camera on every now and then when something vaguely interesting was happening. So I'll just show you some footage from those early clips, and then I'll catch up with you at the present day a little bit later on. God, this sucks. The lead screw in the Z-axis keeps slipping out of the bracket that I made for it. It's kind of useless actually. Alright, that's enough. The pen is moving a little bit in its mount, or what do you call that little hole that it pokes out of. So that's why the back of the C, the back of the C's don't line up, because they're approached from different directions. But if we run this again, we should see it running over at the same spots. So it's going to be crooked in exactly the same way, which is all we really care about at this point. So here's the result of that. Each one of those was done 3 times or 4 times. I think the one on top was done 4 times, but there's not really any evidence of the pen having gone in a different place each time. It's not perfect because the pen is moving within its casing a little bit, so the back of the C sometimes doesn't match up. That curve at the back of the C there. Overall, I think it's perfectly adequate for what I need it to do though. Okay, let me show you the procedure that I'm using to generate the G-code for the soldering job, and I'll also show you this nifty little jig that I made. This is a 6mm aluminium plate, and I've drilled some holes into it and machined some pockets there, and these are perfectly placed and at the right depth so that when you put some pins in here, well, some female headers in that side, and then you try and place an I/O mixer board on top like this, everything will line up perfectly and it will sit in there. Obviously this one's been soldered already, but you would put in one that has not been soldered like that and press it up against that side and then that side, and it should be perfectly square. And the way that I made all those holes was by exporting from EasyEDA. You can export to DXF like that. So I exported my board plan, and that gives us a file like this with a whole lot of stuff that we don't really need, but you can come in and select just these circles and delete everything else. So that's how I made the G-code to drill that aluminium plate. And to do the soldering job, I'm doing something kind of similar. I'm starting with that DXF and deleting everything that I don't need apart from these, which are the holes or the pins that need to be soldered. And I've colored them red and green, where red is a ground pin and green is a normal signal pin, because the soldering iron will need to dwell on the ground pins a little bit longer. So we need to differentiate them. And up here you'll see this one has a little red cross in the middle. That is the 00 location of this frame of reference. So this DXF file is just a text file, and if we look at that here, we can copy and paste that and put it into a little tool that I made called Solder Planner. It's very crude at the moment. It just looks for circles in that DXF file. That's all it does. And so the purpose of this tool is so that we can click on these dots and define which pin we want to solder in which order. And this is a little bit important because you have to think about how the heat is going to be moving around in the board. But anyway, let's click on some of these and you'll see that there's a little line drawn between them and they show up something like that. So just for this little demo, I'm just going to do those 11 pins there. We click Generate Plan. We'll see some G-code. Yes, this is actually G-code. Might need a little bit of explanation though. LinuxCNC has these things called O codes, which is basically like a function, you would probably call it in most other programming languages, or a subroutine, or a stored procedure, or something like that. And the one that I'm using here is called poke pin, because what we're going to do is we're going to take the pin and we're going to move over the top of each of these pin locations, and we're just going to move it down and up again to give that pin a little poke. We're not going to touch it, we just want to come close to it to see that we're in the right location. And so we're going to call that subroutine, and we're going to pass these three parameters, which are the X and Y location, and then the 1 or the 0 for the third parameter specifies whether it's a signal pin or a ground pin. So let me copy this into a text file where we can run it as some G-code. And I have a file right here, which is just a like a skeleton of a G-code program, and I'm going to paste that into the middle and save that file. So this poke pin, the function itself, is defined in a different file, this file here called poke pin. And if we have a look at that, we'll see that this scripting language, or whatever you want to call it, it's a little bit hard on the eyes. It's got all these hashes and square brackets, and it's a bit ugly, but I guess like everything, you get used to it after a while, and then it starts to look a little bit normal. So just to briefly look at what we've got here, the first little bit here is just some comments, and this is just to remind me of what the parameters are that I'm expecting. Then we have some values that I've defined. So we've got a clearance height and a poke height, which are 1 millimeter apart. So the vertical movement's just going to be 1 millimeter, just a very small movement. And then we have a dwell time in seconds for each of the ground and signal pin types. 3/4 of a second for ground, and then 1/4 of a second for signal. In reality, when you're actually doing some soldering, these would need to be longer, but I just want to make the demo run a bit quicker. And in these subroutines, we can do things like branching with an if statement, and we can do loops and all kinds of other stuff, and we can also call other subroutines. So it's really quite a powerful feature when you look into it. And then these last 5 lines here are the actual movement G codes. So we're going to move up to the clearance height, or we're going to move to it, and then we move horizontally to the XY location. Then we're going to move to the poke height at that speed, and then we're going to wait for whatever the dwell time is, and then we're going to move back to the clearance height again. So let's have a look at that running. And I've got so many windows here. So the way I've set this up is, whoops, are we on? Okay, we're on. So the way I've set this up is I need to jog my soldering iron. It's just a pen at the moment, but I need to jog that to the 000 location. And it might not look on camera like it's exactly over that pin, but I assure you it is pretty much. Alright, so that's going to be 000, and I have a little hardware button over here that I'm going to press to touch off so that X, Y, Z all go to 0 like that. And then, oh, I was just about to run the program, but we haven't loaded it yet. Hold on. So it's this foo is our file. So there's our 11 pins, and we just run that program like this. And you'll see the last pin in each row was a ground pin, so I'll just run that again so you can see that the last pin in each row is a little bit slower. So I'm quite pleased with that. It all seems to be working pretty much as I expected. And the next task, I guess, is to set up the soldering iron itself, and then I'm probably going to be spending hours twiddling around with this subroutine, figuring out how long it needs to dwell for, and whether I can just poke the soldering iron straight in, or whether I need to come down and then sideways a little bit, and all that kind of stuff. But the beauty of this system is that the definition of what to do at each location is separate from the list of locations like this. So if I have a different board in the future with a different layout, I just need to change this file, and I won't need to bother coming back and retuning, or copying and pasting this into a different file, because it's sort of a subroutine that exists by itself. And just to show you how easy it is to change, I was going to do something here. So we're moving up and down vertically there, but if I just take out these two parts where it was doing the vertical movement, so this is the Z part. I'll just comment those two out and save that file, and then we will run it again, except this time it's not going to go vertically anywhere. So that's actually a quicker way for me to figure out whether everything's in the right place. But yeah, it seems to be going fairly well so far. This is what the full run looks like, if you want to have a look at that. Okay, I have the soldering iron stuck on there now, and I'm just setting up the relay that will let LinuxCNC turn it off and on. So that's done with a relay like that, and just a few wires going into the real-time unit. And on the other side I have a LiPo battery to power the soldering iron, so it's just going to turn the power from the LiPo battery off and on to the soldering iron. And we do that by issuing an M64 to turn a digital output on, and then this P0 is which one. P0 just means the first one, which is what we have the relay connected to. So we turn that on like that, and you'll notice that the heat comes on immediately. That is not the default behavior of these TS100 soldering irons. I had to change the firmware to something called Iron OS, which gives you a lot more options, one of which is just to immediately start the heat. So normally I would have to push one of these buttons to get the heat to start, but I didn't want that because I wanted LinuxCNC to be able to turn it off and on completely. Anyway, so to turn it off, we do an M65 P0 like this. There we go. So we can control that completely scripted. To feed the solder wire through, that's the tip of the solder wire there, and if I just jog this manually, this is the A axis of the CNC system. So I'm just jogging that in and out a few millimeters. I ended up using an off-the-shelf 3D printer extruder. Initially I made my own, but that didn't work out very well, and I just had to face reality and buy an off-the-shelf one. There's a few too many specialist parts required for this. To get the solder to go in the right place, I'm using this, I think they call them Bowden tube, and it's made of a very, very low friction material, PTFE I think it's called. And I'd heard that this was low friction, but even so, I was very impressed at just how low friction it is. So if you look at the other end there, I can hold this solder. It's 0.8 millimeters thick solder, so it's quite soft and flexible, and yet all the way from out here I can still push it, and it doesn't want to like kink up in the middle here because there's just no friction on it. It's really quite impressive how low friction it is. And the other end of this, as you can see, is held out on this exquisitely crafted arm. And on the end of the arm we have a screw here which lets us, if I can just break that free, there we go. So we can have a little bit of flexibility in the movement. And then this screw on this end also lets us turn this around. Hopefully I can do this without, there we go. So we can turn that there. And then this one pinches this little aluminium tube. So it's all very small and delicate, and this tube is quite prone to bending, so I have to be careful with that. But I wanted this piece to be aluminium for a few reasons. One is that it's going to make the last part of the solder nice and straight. So we don't want it coming out of the tip going in curved or in some direction. We want it just going in a straight line out here. The other thing is that the tip of it's going to be in a fairly hot area, not too far from the soldering iron, so I didn't really want it to be plastic. And if this tip does get kind of warm, the aluminium being such a good heat conductor hopefully will just transfer that heat away and up here fairly quickly. This block, there's a couple of holes there. I thought I might have to tap those holes and put a little screw in there to clamp these pieces together, but it turned out to be not necessary. I just push them in and they contact, or they sit in there and stay where I put them quite nicely. Okay, this is the result of my first board soldered. I just did this a little bit at a time, adjusting the parameters as I went, so they're gradually getting better as we go around. There's only a couple that didn't get soldered. That ground pin right in the middle of the frame there, I tried that about 10 times. I don't know what the problem was. I'll have to do that manually. I just gave up on it. And that pin there right about the middle of the frame too also did not connect, I think. All the other ones connected, although that one there, not really much solder on there, so I'll have to fix those. And obviously we have a whole bunch of bridges where there's just too much solder on. It's kind of hard to strike a balance between getting enough solder on there to help the heat flow between the pin and the PCB and having too much solder like that. But as a first run, I'm reasonably happy with that. This is what the pins look like before you put the board on, by the way. So you put that on there. I'm not going to be able to do it with one hand, but you've got to just jostle it around and eventually it'll pop on quite nicely. Okay, this is the second board that I did, and amazingly I was able to do this without changing any of the parameters all the way around. There's just one pin that didn't really connect there, and there's a bridge there. Everything, oh, that's not very good either there, but everything else is okay except for a couple of times I had a problem. One was that the LiPo battery I was using started to get very low and I didn't want to damage it, so I had to stop halfway through. And the other problem was that the A axis, which feeds the solder in, reached its limit because it just goes in one direction all the time, and I had a 1 meter limit, and so it got stuck on that and I had to restart it. And each time I restarted the program, I had to go into the program and comment out the pins that I've already done so that they don't get repeated. Because if they get repeated, they get twice as much solder on them, like what happened there. So that is actually not, wasn't like that to start with. That was just because of my other disruptions that were going on. So I think what I'm going to do now is I'm going to put another board in there, and I'm just going to do full send, do the whole thing without stopping. And amazingly, I don't feel like I need to change any parameters. I thought I was going to be twiddling with those parameters all day, but basically with that first board I did here, just going around once carefully, seems to be pretty good already. Alright, so here's the result of that uninterrupted job. It's looking pretty good. There's just 3 bridged parts there, and that pin there somehow ended up completely dry. It's a bit of a mystery, but the rest of them look quite nice actually. Was it? Oh yeah, no, they're fine, yeah. And so that took just under 10 minutes. That's including 28 seconds for the soldering iron to warm up, which I think I'm going to have to wait for every time because the soldering iron doesn't really have any way to give me any feedback about when it's up to temperature. So we're just going to have to wait 28 seconds even if it's already hot enough to continue. But yeah, that's quite nice, and I'm not sure really how I could improve with the parameters. It looks like that's about as good as I'm going to get. So I think I'm always going to have to end up, doing a little bit of fixing of things like these bridges and dry spots. But this gets like 95% of the work out of the way for me. Okay, my next task is to tidy this all up and make it a bit more user-friendly. So we're going to put all that stuff, I'm thinking we can fit it underneath there, and I'm going to add this control panel on the side. But I was just editing some of this video and I realized that I've come all this way without even really talking much about the design of the thing itself, which some people might be interested in. So all the parts are made from aluminium, as you saw earlier, and I'm using these linear rails and belt drives all around. The large rail there is an MGN15, then we have an MGN12 here, and then we have also another MGN12 up here for the Z-axis, although I did not start with that. I started with something else that did not work out very well, which we'll look at in a minute. So yeah, just one carriage for each of these. I figured there's not really that much load on it, so it's just the one, and then underneath, under that, there you can see just one carriage there. And on this one here I had to make a lot of countersinking to make sure that the top of it was flat where those bolts go in, but the other one wasn't so difficult. And all of these belts here are being driven by two NEMA 17s that fit underneath. So you've got 40mm clearance here, so I forget what size they were, but I think they were the 34mm ones. They could have been a little bit smaller, but what I've noticed is that it's not usually a problem to have a larger motor than you need, but it's definitely a problem to have a smaller motor than you need. So I went with 17s there because I had a bunch of 17s sitting around as well. Now this belt system here, people might have been looking at that wondering what's going on, but the way these belts work is the motor on the right with this belt moves this central plate back and forwards like that, and then this motor goes through a sort of a pulley, and then it comes through to the top of the plate there on another pulley. So we've got this system of two bearings and a toothed, tooth pulley and two idlers, and then underneath is the same, but it's at 90 degrees to that. And the purpose of that is to transfer this motion through the plate to the underside of this main table without having to have the motor itself stuck on the end. So the alternative was that that motor would be stuck on here somewhere. So it would either be stuck on the top with a big ugly lump here, or it would be stuck on the bottom, which may be slightly less ugly, but then this plate would have to be a whole lot higher. So instead of being here, it would be up here, and it would just look stupid. So I thought I'd try this, and it worked out quite a bit better than I expected. All the tolerances or the clearances are very, very tight. You can see that one at the bottom might look like it's touching there, but if we just put a piece of paper in there, you can see it's not. So all the way along, it just doesn't quite touch, which is perfect. And to get this to work, the main thing is that pin in the middle, which goes from one side to the other. So it's just a 5mm steel rod that goes through. And the crux of it all is that the bearings, there's two bearings there, one on each side. They're little bearings like that, not quite those ones, but something very similar with a flange on them. And they had to be seated very, very carefully, so I just crept up on that with my CNC machine when I was making that plate to get those two bearings to sit in perfectly. There was still a little bit of play in that shaft as it goes through on each side, but when you put the belt on and tighten it, that play goes away. Other issue that I had to deal with was how to get these belts to connect to the table or the piece that they're supposed to move. And as you can see, one way I've done that there for this belt is I made a little piece of aluminium with a slot in it, and that has a threaded hole on one side, so it pinches the belt as it goes through so that the belt cannot move. And I was able to do that there, and that was quite nice. And it doesn't damage the belt in any way because the belt's just being pinched, it's not being pierced. But for this one, where the belt goes alongside there, I couldn't really do that because the whole thing's underneath. So what I ended up doing is I used a little aluminium block like this, just a little small piece, a little bit smaller than that actually. And the second, or so the main four screws here hold the table to the carriage. Then those other screws at the back are holding that aluminium block on to the bottom of the table. And then I discovered that you can actually pierce these belts, put a screw through them like that. I just did this as a test. I didn't think it was going to work, but it turns out you can pull very hard on that and it doesn't go anywhere. It doesn't rip or tear or give, or it's just perfect. So when I discovered that, I'm pulling on that quite hard and it's just not even moving. So once I discovered that, yeah, I thought I'd just do that. So that's how the other side of the table's going. Oh, we can actually see, maybe you can see that here. We have a similar, oh, there we go. So this is done in the same way. So those two screws are just going straight through the belt. It makes the belt a little bit wider there, but it doesn't seem to really matter. And yeah, so far it's been working quite well. The nice thing about this little machine is that there's not really any stresses on it much. It doesn't need to move fast, or it doesn't need to be powerful. So you can take a lot of shortcuts like that. I don't think I would have done that trick there with larger belts. So like on my larger CNC, I wouldn't do that. To tension the belts at the other end, I'm using a couple of small bearings like this, these flange bearings again. And I discovered that if you put them on top of each other with one or two washers in between, they become just the right width to hold that belt quite nicely. And more importantly, you can put a screw through here and you can tighten it down as tight as you like, and somehow they still roll nice and freely. I guess the piece in the middle is just a little bit higher than the outside of it or something. But anyway, they've been working beautifully like that. And the block that they're going into, that pill-shaped or capsule-shaped thing, there's a slot underneath where that block can slide, and then I have 2 or even 3 screws that can fix it in place. And in other situations where we want the belt to be closer to the surface, so this belt's about sort of 12 millimeters above the main surface there, but if we want it to be lower, we can cut out the cavity on the back and have that block sliding in and out like that. And that's what I've done on here. So you can see there just the block sticking out the bottom, and there's a slot where it's sliding into, and a couple of screws there to tighten it. So the screw in the middle of the slot is holding it, and also the screw that's inside the bearings is holding it as well, so it's not going anywhere. So this whole bottom section here for the XY movement has actually been working quite well. I thought this would give me problems because of this funny system I've got with the belts, but no, that was okay. And all my problems actually have been with this section for the Z movement. So let's have a look at some of my failed designs, because I had to go through this 4 times before I got one that worked. Initially I was going to use, that's my first plate there, and I was going to use this little NEMA 8 motor, which was going to poke up through there, and there would be a belt tensioned like I just showed you earlier, and it was going to slide on the rail there, which was this cute little MGN 7 rail. And I figured this would be appropriate because I kind of like to make each one like go down in size a little bit as the movement gets smaller. So that's why I use this one, and just a single clamp to hold the soldering iron on. But this immediately, as soon as I got it, I began to think that it probably wasn't going to do the job, because I'm not sure if this is a fault with this particular one, probably is, but what would happen is it would slide okay for a bit, and then it would just get stuck, and it seemed like the balls weren't going into their recirculating channel properly. I took it all apart and cleaned it thoroughly and greased it up and everything, but it just wasn't having any of it. It's very unpredictable. It would work okay for maybe a minute, and then it would just get stuck. And when it got stuck, there was no way in hell that this system with the belt was going to be able to unstick it or push through that sticky spot, because when you're using a belt, the side of the belt is like 5 millimeters away from the center of the axis, so these motors are pretty gutless. It just didn't have the power to turn it with the belt. So I figured if I went to this, so this is my, that's my 3rd design actually, so this is my 2nd design. I needed to go a bit wider on this plate because I changed the extruder, so that's a little bit wider. So this is the 3rd one, and after I changed to using a screw drive like this, you can actually buy 4mm threaded rod like this with a nut, especially for this purpose I found, so that's quite nice. It worked a lot better, but it's still sometimes, even like this, like it moves alright most of the time. But even like this, with the extra torque that it was able to get with the screw versus the belt, it would still get stuck sometimes, and I just got sick of this silly little rail, and I ended up getting an MGN 12, so that's what we've got there, same as on here, because this one was beautiful, nice and reliable, and I just got sick of this. Another problem was that this clamp here, only with a single clamp, the soldering iron was able to move a little bit. So in my current design, you'll notice that that plate there, we've got a clamp at the bottom and at the top, all the way up the other end. It looks a bit goofy because we've got this huge plate in between that needs to be there to hold it together, but it does work a lot better, and I'm happy with this. And we've gone back to belt drive, but the reason I'm able to use the belt drive here and it doesn't matter is because we have a NEMA 17 on the back now, and completely given up on these NEMA 8s. They just don't seem to be good for much at all, at least not in this context. So the extruder that I ended up using is just a regular off-the-shelf one running off that NEMA 17 like you'd have on a 3D printer. But initially I rather naively decided that I was going to use this gutless NEMA 8 motor to do it, and I was going to design my own extruder. So I made all these parts here on my CNC router, of course, and it fits together nicely, and there's the parts at least turned out how I expected. But unfortunately, this was just never going to work. So the idea was the motor shaft in the middle has a bit of silicone tubing on it, which was supposed to provide the friction for the solder to move through. And it was just going to be pressed against by the aluminium shaft on the side. And at this stage, I had not actually looked at how these extruders work, but they usually have two motorized sides. So what I've got here is just the center shaft is going to turn, and then the cylinder on the side doesn't have any power. It's just a roller that's pressing against it to provide friction. But if you look at those off-the-shelf ones, they have both of those rollers are physically forcing the filament through. So that's what I needed to do, it turns out. And this motor was just pathetic. Like, it was never going to do it. So I just gave up on that, and I have a regular extruder in there. And the only thing I had to do to that, apart from filing off a whole bunch of things to get some clearance for parts of it, is I had to put some soft silicone tubing like this on the rollers of the extruder on both sides, because the solder that I'm using is only 0.8 millimeters thick, and I guess 3D printed filament's usually quite a bit thicker than that. So the steel rollers themselves were not able to even contact it. It was just sliding through with no resistance at all. But when I put some of this on each side, and I also had to modify the springs of the extruder to squeeze it a little bit less. But anyway, it works reasonably well now. It still slips a little bit, but that's actually kind of a good thing, because sometimes I've noticed if the heat hasn't quite gotten into the pin properly, when the solder comes out and it presses against it, because it doesn't melt, it just gets stuck. So in that situation, we don't want to have a super strong or super good friction on the extruder to just like keep jamming that solder in while it's not being melted. So it's actually kind of good that it will slip when that happens, what I've noticed. So that's quite good, I think. And I just realized we haven't even looked at this from the left-hand side yet, so let's do that, or the right-hand side, whatever this is. So that extruder is just a store-bought one. And I had to file away a little piece of it, or quite a bit of it there, so that it would clear once you put the silicone tubing on. And I also had to drill and tap a hole here so that I could stick a piece of aluminium angle in this case. But I just needed to stick a piece of something on here, because that silicone tubing there, it's amazing how quickly it will just walk off the end and fall on here and become useless. Literally in about 2 seconds, it just goes whoop and it falls off, which was very annoying. But once I put this blocker here to stop that, it was okay. And the spring has been cut down to about 2/3 of its size. I can't remember exactly why I needed to do that, but I think it was probably also related to the fact that once you put the silicone tubing on both sides of this, it's quite thick tubing that I showed you already, didn't I? And once you put that on, the spring, as thick as it was before, just wasn't really working out. And I also found that this motor, you couldn't use a wimpy little small one. So my first plan was just to use these really thin ones that I got, because that would mean that I could use the other, the thinner Z plate here that one of my earlier designs. But it just wasn't enough power, enough torque with this motor. So I had to go back to using this, which is rather a larger one. Was that 34 again? I think this is the same as the motors I have on the bottom. These ones here are the same size. And that turns the extruder quite nicely, actually, once you do that. So on this side we have that little bit of PTFE tube going in there, and I just poke it inside the extruder. I think I might have had to drill a little bit out of that too, But I just poke it in until I feel it stop, and then I back off a tiny little bit, and that seems to have worked out okay. So this PTFE tube is going in all the way up until right before the rollers. And on the back we have this funny looking thing, not really sure what that's for, but it has a sort of a clicky, like if you push that it makes a clicking sensation. Can you tell I'm not a 3D printer person? And then it just pulls the solder off the reel like that, and that seems to work alright. It would probably be better if it was up a little bit higher so it wasn't turning the corner quite so sharply, but so far it's been fine. And I guess the only other thing that I'll mention is that you need to keep in mind that this PTFE tube should not be moving backwards and forwards, and the way I've done that is this little piece of plastic that came with this tube when I ordered it. I don't recall buying that plastic. I think they just put it into the package for me, and it seems to be sized quite nicely so that you can slide the PTFE tube in, and it has a decent amount of friction so that when you let it go it will stay there, and the solder being pushed through is not strong enough to break the friction between this pipe and this little piece of plastic. So that's the only thing that's holding it in place when the extruder moves. The PTFE tube does go into the extruder itself all the way to about here, but there's no friction in that area really. So yeah, that was necessary to hold the PTFE tube here, still here, and it might look like it's touching that belt, but it's not, and probably wouldn't matter anyway because it's quite low friction. So now I need to tidy away all this stuff underneath the platform there, but let's just have a look at what it is first. So this thing here is a programmable real-time unit that is going to be controlled by LinuxCNC. LinuxCNC is going to be running on the Raspberry Pi there. And this board here, if you haven't seen it already in my previous video, I know it's hard to believe, but not everyone has watched all my previous videos, but I'll put a link in the description to that if you want to have a look at what that is. And it's being controlled by LinuxCNC, which is running on the Raspberry Pi here. I've been using this Raspberry Pi 3 for most of my testing and tweaking all the settings, because you need to do a lot of stopping and starting of LinuxCNC, and that's kind of slow on the Raspberry Pi 0W, which is what I'm going to eventually be using. But now I've got all that testing out of the way, I'm going to be replacing that here. And I think for the day-to-day running of the job, it should be fine. It's just that running the graphical user interface and that's a bit slow. And also, I'm not quite sure it's going to fit in there very well. It might just fit, but it's going to be really tight. So hopefully I don't have to use this for the actual, final finished thing. Then we have a bunch of inputs over here. There's a switch which I'm going to use to enable or disable jogging. Jogging is going to be done, some of these things are going to go on this panel here, so that switch is going to go on this panel, and this panel is going to stick on the side like that. So jogging is going to be done by this joystick for the XY, the main platform, and then this is going to be used to jog the vertical, the soldering iron up and down, and then if I click it like that, it will switch to jogging the solder extruder, again just like that. And then this switch, whether it's on or off, will enable or disable those two joggings so that I just don't bump it or move it by accident or whatever. Then we have three simple press buttons, and they're going to be to start the job, stop the job, and the one in the middle will be used to touch off. So what I'll need to do, at least after turning the machine on each time, I'll need to use these to jog into the starting position, like the 000 location in the work coordinates, and then I'll press this middle button to say that, boop, that is where 0 is, and then I'll just be able to run the job after that. This encoder, oh well, that's going to be my encoder over there. And then we have the relay, which turns the soldering iron off and on, and that's just coming through XT60. I'm planning to use a laptop power supply to run this on 18 volts rather than the 4S battery that I've been using for testing. And that 18 volts will also go into power the stepper drivers. At the moment I've been running that on a separate 12 volts on here, but that's going to, so there's just going to be one power input. Oh, and we also have these little RGB LEDs that we're going to stick onto the side of the panel there to show us a little bit about what's happening. These are the tiny little 2mm by 2mm ones. Very nice and cute little weeny LEDs, aren't they? I have been using these 5 by 5mm ones for my testing, but why would we want such clod-hopping great LEDs when we could use these cute little weeny ones for our cute little weeny soldering machine? By the way, I'm sure some of you have noticed that this machine does not have trivial kinematics, And trivial kinematics just means that there's a direct one-to-one relationship between a motor and a direction of movement along an axis. So for example, if you have an X motor, when the X motor moves, the machine moves in the X direction. When you have the Y motor moves, the machine moves in the Y direction. But that's not actually what happens here because, well, if I hold this one still and move this motor, we do actually get direct one-to-one movement in a single axis like that. But if I hold this one still and I move this one, you'll see that we get diagonal movement like that. So this is not trivial kinematics. But fortunately, LinuxCNC, as I said in an earlier video, lets you customize things up the wazoo, and that's what we're going to do a little bit of here. So let me show you how that's done. So to add a new type of kinematics to LinuxCNC requires you to create a custom component, which might sound a bit daunting, but it's actually only a case of changing 2 lines of code, at least for what I'm doing here. If you're making your own 6-axis robot or a Scala kind of system or some other complicated kinematics, it's not going to be that easy. But for me, fortunately, this time was very easy. So all you need to do is copy and paste this file here. So this is the trivial kinematics that we're going to start with, and you can find this in the LinuxCNC source code somewhere. So I've just copied that into a file that I've called weenykins.c, and we're just going to change a little bit of it. We only need to look at these 2 functions here, kinematics forward and kinematics reverse or inverse, and these are the 2 functions that do this calculation that we need to change. Kinematics forward means that we take the position of the joints, or when it says joints, you could consider that to be the motors. What are the motors doing? So we look at what the motors are doing, and from that we can calculate the position in X, Y, Z that's going to result in the machine moving to. And for trivial kinematics, it is very simple. We've just got X, Y, Z directly related to joints 0, 1, and 2. And then for the kinematics inverse, again, 0, 1, 2 just goes straight to X, Y, Z. So that's very simple. And now I'm just going to do undoing a little bit. I'm going to undo a little bit. So I'm going to change this here with my undo, and you'll see what I've changed that to. So now the X position is determined by both joints 0 and joint 1. Should have a bracket there as well. There we go. So that's what I had to change that to. And then in the inverse kinematics down here, if I do a little bit more undoing, I changed that to be X minus Y, because the sideways movement is going to depend on what the up and down movement, at least if we think about it in the terms of the video that we just looked at a second ago. So that's all I had to change, and to be honest, I did not quite know which way I needed these to go, so I just did a little bit of trial and error. It's about a 50-50 chance whether you're going to get it right, so I just tried it until I got what I wanted. And then to install that into your LinuxCNC system, you would do sudo hal compile install and then whatever you called your component file, and that will compile that file, and it will create the shared library and install that into the LinuxCNC system for you. To use your new kinematics, you also need to modify your ini file, which is the main settings file that determines most of the major settings of what your system is going to do. And you can see that I've commented out trivkins, which is probably what it will be by default if you're setting up a new basic XYZ kind of system, and I've just replaced that with Weenykins. So that's how that's done. So I just mounted everything on a piece of plywood like this. It should be fine. We've got that there and the relay, and we've gone back to using the Raspberry Pi 0W. It fits in here a lot better. Plenty of room now that I'm using that. This is mounted up here, nice and solid. And the wiring is a bit of a mess, but I think it'll tidy up okay once the top goes on. It's going to have to be squashed down a little bit. That should be alright. I got a little bit lazy. I didn't make any plugs for these wires. I just soldered them straight onto their pins where they're supposed to go. And I found a way to start up LinuxCNC automatically without needing to use remote desktop. So you plug the battery in and wait a few minutes, of course, for the Raspberry Pi to start up. And then LinuxCNC will start up, and it will turn off the e-stop, turn the machine on, home the machine, and load the program that I need to run. And then these lights will come on to let me know that that's ready, and I can do my jogging and start the program. So let me get all this packed under here, and then I'll show you that. Alright, so everything's looking much tidier now. Just got this plug sticking out the back, and the soldering iron connection, I've disconnected that for this little demo. I don't really want the soldering iron running. I'm just going to run everything off this 18650. This is just a 3-cell pack, but we will plug it in like that. So these lights come on, those are just directly connected to the power. But these other lights here on the left, they will turn on when LinuxCNC is up and running and the Raspberry Pi is connected to the real-time unit and everything's ready to go. And I'm using a cron job to do that. I am aware that there are other ways to start up things automatically on Linux, but for some reason the LinuxCNC startup script didn't want to work unless it had the environment of the Pi user. So normally for something like this I would use the root user, and you need to specify full paths and everything when you do stuff like that. But for whatever reason the LinuxCNC startup script just would not work as root user, so I'm using the Pi user and I'm using the cron job as well. So I'm using the cron job in the environment of the Pi user to get this to happen. Anyway, I'm just kind of waffling a little bit while I'm waiting for it to start up. So there we go. So you saw the lights come on there, and now we can jog the table. I slowed this down a little bit too, this jogging, but hopefully you can see that it's jogging there. So I would jog this into place, and then vertically I would, sorry, the movement's a little bit slow, but hopefully you can see the soldering iron going up and down there a little bit. So when I get it to where I want it to be, then I can lock my jogging so I don't, now when I try and jog it, there's no jogging, and that does nothing. Or the other thing I'd probably have to do is make sure the solder is in the right place. So to change between jogging the soldering iron and the extruder, I push this button, and that light there will change from green to yellow. Hopefully you can see that there, yellow. And so now you're not going to be able to see the solder moving, but I can make sure that that's in the right spot, and then lock everything. Then press the middle button to touch off as 000, and then press the green button to run the job. And when everything was started, it also loaded up that program that I need to run as well. So it's all very convenient and doesn't need any Wi-Fi, which is nice. It's all self-contained on the Raspberry Pi, and I'm not even sure that the Wi-Fi would work very well now that it's under this big metal plate and it's got a fairly thick piece of wood on each side of it. So far it has not having any problems, but just in case it did have problems with Wi-Fi, it's nice to know that it actually doesn't need any Wi-Fi. It's all just self-contained here. However, to turn it off, I do kind of need Wi-Fi, because I'll need to SSH into it to shut it down properly, because I've discovered that it's not a good idea to just pull the plug on a Raspberry Pi, because you might corrupt the SD card. So I will need Wi-Fi at some point just to turn it off. And I'm planning to run this on battery for a while. Not this battery, I have a larger one for the twin hopper. It's I forget how many watt hours that one was, but this pack here is about 165 watt hours, and I measured the current that this draws when it's on standby, not doing any soldering, just waiting. It's only 2.1 watts, so this could stand by for about 80 hours or 3 days or so. Of course, as soon as you start doing some soldering, it goes up. It's about 20 to 25 watts when you're actually doing the soldering, and then slightly higher than that when the soldering iron's climbing up to the desired temperature. But anyway, eventually I'd like to run it from a laptop power adapter that runs at 18 volts or 18.5 volts, which is very conveniently around about the storage charge of what a 5S lithium ion pack would be. So I'm thinking I might make a little UPS so that if the power gets cut, nothing will go wrong with this and I won't corrupt the SD card, and the job will just keep running. But that's going to have to be a future video, because this one's too long already, and I think I'll just leave it here. I don't actually have any more IO mixer boards to solder. I was planning to make a little demo at the end, of course, to finish off the video, but I'm all out of them now, so I'll just have to finish it here. Thank you for watching. See you next time.